Hi, so in this video we are going to look at a relationship between the Einstein coefficients, or how we relate them. Now this is a continuation of my first video on Einstein coefficients. So if you don't know what the Einstein coefficients are, you can either watch that video or look in the textbook, which is probably the better option. So how do we relate the Einstein coefficients? Well, we use the principle that the Einstein coefficients A12, B12 and B21 are independent. My spelling is totally wrong. I'm dyslexic, by the way. So Einstein coefficients independent of the field, and this means we can choose the radiation field in such a way that it makes our lives easy. Now the easiest radiation field that I can think of is the black body radiation field. So that's going to be our first assumption, that we have a black body radiation field. We're also going to assume that we're in thermal equilibrium. Thermal equilibrium, where this kind of odd sign here is a shorthand notation for equilibrium. I think that's actually kind of an old school way of doing it. And we're going to make a third assumption, and that third assumption is that our line profile, phi omega minus omega 1, 2, which omega 1, 2 is called the central frequency, and we're going to assume that is equal to a jet delta function, delta omega minus omega 1, 2. Just to point out, this phi is also called g in some textbooks or in some sources. You may be wondering, can I just give it a coefficient of 1? The answer is yes. When this is integrated over, by definition, it gives you 1. When this integrated over, all omega, by definition, it gives you 1. Therefore, the coefficient of 1 is correct. They are our assumptions, and they are what we are going to use to find a relationship between these Einstein coefficients. Okay, so let's draw our level system. We have two levels of interest, level 2 and level 1. We may also have some other levels, like a level here called level 3, and we have 3 transitions between these two levels, and if you watched my last video you may know what they are. We have absorption, which takes an atom or electron from level 1 to level 2. Stimulated emission, which takes an atom from level 2 to level 1. And spontaneous emission from level 2 to level 1. Now, in thermal equilibrium, the number of atoms going from level 2 to level 1 must equal the number of atoms going from level 1 to level 2. That means that these 3 processes must add up to give 0. Or these 2 processes must equal this process, or the number of atoms that undergo in this process. You may be wondering then, what happens if I have transitions from level 3 to level 2, or from level 3 to level 1, or vice versa? And it actually holds that what I just said about these transitions still holds. So the number of atoms going from level 2 to level 1 must equal the number of atoms going from level 1 to level 2, regardless of what's happening with other levels. This is a principle called the principle, again my spelling is going to be wrong, of detailed balance. This has some other names. It's also called, I don't know how to spell balanced, that'll do. It's also called the principle of entire equilibrium and the principle of microscopic reversibility. Okay, so we are going to use the principle of detailed balance to say that these 3 processes must add up to give 0, or that they must equal. So we look at the number of atoms per unit volume per unit time undergoing absorption. And we wrote this down in my last video. Actually, I'll do it in this car. This is equal to N1 times by rho omega 1 2 times by B 1 2. This must equal the number of atoms undergoing these two processes. So that's equal to N2 rho omega 1 2 times by B 2 1, where this is the number of atoms per unit volume undergoing stimulated emission per unit time, plus the number of atoms per unit volume per unit time undergoing spontaneous emission, this N2 A21. Now I've used the fact we have a jet delta function here. This rho omega, technically it should be an integral of rho omega times by phi omega d omega. But since we have a jet delta function, it just goes to omega 1 2 by definition of the jet delta function. Okay, so we now have these relationships, and I think it's time to go back to our assumptions and see what we've used. We have used that we are in thermal equilibrium. The principle of D-head balance works only in thermal equilibrium. We've also used this jet delta function. So what we're left to use is this black body function. So we're going to rearrange this, but we're not going to rearrange it in the way you might think. You can rearrange it in the way you might think, i.e. making rho omega the on one side by itself. We're not going to do that. What we're going to do instead is we're going to make the ratio N2 over N1 by itself. This just makes it slightly more convenient for us later. So we have that N2 over N1 is equal to rho omega 1 2 times by B 1 2 over rho omega 1 2 B 2 1 plus A 2 1. So that is that relationship, and we don't need these pictures anymore. We are gonna divide through by rho omega 1 2 to get us that N2 over N1 is equal to B12 over B21 plus A21 over rho omega 1 2. Now we're going to use the assumption we're in black body. We have a black body, and we're going to sub in that rho omega 1 2 is equal to h bar omega 1 2 cubed over pi squared pi squared t cubed times by 1 over e to the h bar omega 1 2 times by beta, where beta is 1 over kbt, minus 1. That's quite a complicated equation. If you want a derivation of that, there's one on my website, which I will link to in the comments. Or you can look in the textbook, which, like I said, is probably better than like what I can do. So we sub this into here, and we also use again the principle that we're in equilibrium. And because we're in equilibrium, this must be given by the Boltzmann distribution. So the N21 or N2 over N1 must equal G2 over G1 times by e to the minus beta h bar omega 1 2. That's from the Boltzmann distribution, and that's from the assumption that we're in thermal equilibrium. So we're going to sub these two into this equation to give us that G2 over G1 is equal to, we'll put the exponential in as well, e to the minus beta h bar omega 1 2 equal to B12 over B21 plus, and now I'm writing actually the inverse of this, so that's going to be pi squared c cubed over h bar omega 1 2 cubed e to the h bar omega 1 2 beta minus 1 times by a 2 1. That's in it. Like, I know that's quite hard to see, but I'm not writing that out again. Okay, we've now subbed this into here, and we are going to times by the denominator on the right hand side. My rubber just broke. Okay, so we're going to times by this, and that's going to give us that G2 over G1 e to the minus beta h bar omega 1 2 times by b21 plus pi squared c cubed over h bar omega 1 2 cubed times by e, so this is quite a long equation, e to the minus 1 2 beta minus 1 a 2 1, and that has to equal b 1 2. Now we use the principle. Actually, before we use the principle, which I have yet to name, we're going to times through by this, and that gives us e to the h bar omega 1 2 beta. Okay, this is technically independent of temperature. It must hold for all temperatures T. That means because of the independence of the e to the h bar omega 1 2 beta from a constant, we can equate coefficients of this, and we can equate constants. So let's do that. Let's first of all equate constants. We have that G2, G1, B21 must equal pi squared c cubed over h bar omega 1 2 cubed times by a 2 1. And then we also equate coefficients of this exponential. So that gives us that b12 is equal to pi squared c cubed over h bar omega 1 2 cubed times by a 2 1. And then we can equate these two sides to get that g2 over g1 b21 is equal to b21 is equal to b12. And they are the relationships between the Einstein coefficients.